right, and we back. How's it going? What's up? So today is day 8, relearning number theory. Today we are actually going to get through quadratic reciprocity, or my finger is going to fall off. I got a beard hair stuck in my finger a few days ago, and I complained about it on stream, and it is still there. It's starting to look infected. So, if this is it, it's been nice knowing you all. It's been a really fun short run. Next week, I will be traveling, so no streams. And hopefully, I'll make it back alive the next week. So, if this is your first time, welcome. My name is John. I am a mathematics hobbyist, which is sort of a stretch. I studied pure mathematics 15 years ago or so. I was planning on doing graduate school, decided not to do graduate school, worked in Silicon Valley, worked for Apple and Google and stuff. And now I'm unemployed because the entire tech industry is going through layoffs and a downturn. So here I am. I'm relearning mathematics. It is my hobby. It's something I want to do for fun, especially number theory. Number theory is just gorgeous. That's what this series is. Every week, we're cycling, doing different topics each week. This week is number theory. It's my fave. And we're working through this book by George Andrews. It's really terrific. Today we will try again to write down the proof and statement of quadratic reciprocity by Gauss. That is one of the gems, one of the real treasures, one of the most beautiful pieces of mathematics in this entire book. Gauss proved it 6 different times in his life. He gave 6 different proofs of it. Euler, before Gauss, was stuck and never was able to solve this problem. But Gauss got it, and that's why we know and love him. So let's get into it in just one more second. What else? I'm going to review a proof, well, really an exercise from section 1, the first exercise of Tolman. I'm really enjoying this book so far. I think I'm starting to get it. This is the number 1 most recommended, most beloved book on intro to proof writing, which is critical, key, important, necessary to study number theory. My other series are calculus and linear algebra, so if you're just here to build ChatGPT, you might want to go watch those videos. We'll be mixing in some proofs, but they're going to be a little bit more applications driven. This one is for fun. We're not here to harm the world. We're here to study pure mathematics. It's like playing chess. Hopefully nothing evil will come out of it. So let's get started. If you enjoy this, please leave a comment. Please hit like and subscribe. Let me know what you like about it so that I can keep doing more of that. Let me know what you don't like about this so I can stop doing that. I am here to serve you. I'm giving you free content. I am feeding the algorithm. I am doing a good marketing person job on YouTube because you have to use social media if you want to build anything nowadays. So, yeah. Yo, Sam, how's it going? Okay, I'm going to read that and respond to that comment in just a second. I want to pull up the iPad on screen. Enjoying this book. We're going to rework the first exercise. We did it yesterday in a very weird stream, and I'll talk about that a little bit more as we go. But yeah, that first exercise was actually quite delightful. So I think I'm starting to see the genius of this book that everybody talks about. So I'm excited. Yeah. In a sense, this is a reaction channel in the nerdiest way possible. I am here reacting to math books because I'm a freaking nerd. Okay. So think of whoever, I don't know, PewDiePie. I don't watch YouTube. What's his name? Ludwig? Does Ludwig do reactions? I don't think Mr. Beast does reactions. That's beneath him. He's like building burger restaurants or whatever. But yeah, think of I'm like Ludwig, I think, for pure mathematics. How am I doing on that? 1 to 10, let me know. All right, we are going to practice mathematics. Also, I woke up too early and I didn't get enough sleep. So if I seem a little frazzled or thin right now, maybe that's why. So we got coffee with us, pulling up the iPad. Let's get it on screen. I think air server is running as desired. Nope. Where is it? Do we want the iPad vertical or horizontal today? Y'all, please tell me what you think looks better. I think horizontal is better because then you can see. Whoop. Which one is it? This one? All right, there we go. Boom. So, other mathematicians like to draw a cute little square. I like to write the word boom whenever I finish a proof. So you'll see that time and time again. Cool. So let's just do it again. Yesterday, I've started splitting these streams in two because nobody has the attention span. Not even me. Like, this is the most self-indulgent channel ever. Nobody has an attention span to sit through a 2-hour-long math session. So I'm starting to split these. And so the first half is going to be focused on one thing. And then the second half is focused on something else. So in the first half, we're going to do things that are more prepared. And then in the second half, a later live stream, I'm going to be live solving problems and getting stuck and going in circles and things like that. So what we did yesterday, let me just review this problem from Velleman. I thought it was quite nice. This is 0.1. Factor 2 to the 15 minus 1, which is this large number, into a product of two smaller positive integers. Okay, so we can take that kind of straightforwardly. Well, we can easily see that large number, it's right over here. If I circle it again, 32,767 is not even, so 2 doesn't divide it. 3 does not divide it because if you add the digits together, 3 does not divide the sum of the digits. And some of you will know that, some of you don't, so here's your chance to know that. 3 divides n if and only if 3 divides the sum of the digits of n. So I hope that you understand what that little notation means there, if you're following. So if you add up the digits, 32767, that is 27. Oh, wait. Are you kidding me? 3 does divide. Oh, wait. I'm so confused. Yeah. Okay, so they add up to 25. I don't know why I wrote 3 does not divide 27. I think I was in my mind thinking 3 divides 27, not 25. Or I was thinking that 2 plus 5 is 7. Oh, I did it again. 3 does not divide 25. All right, whoops. So here, anyways, we know that 3 doesn't divide n. We know that 2 doesn't divide n because it's not even. 5 divides a number if the last digit is 5 or 0. So then the next prime to try is 7. And we found that 7, using our good old famous, lovely long division algorithm, or you could ask ChatGPT, and you'll find that 32,767 equals 7 times 4681. Cool. So we wrote that again right here. And then part B asks you to find a number that divides. Basically, it just says find x such that x divides this humongous number, 2 to the 32,767 minus 1. So obviously we can't use this same method, just checking every prime. That's going to take a long time, and I don't know how in the world to write out what 2 to 32,767 is. That's going to be a humongous number. So we have to find something smarter than that. And maybe I'll just reproduce a proof really quickly here. 2 to the 32 sevenths, because my work got really sloppy earlier. 2 to that huge number, well, we just found that it is 2 to the 7 times 4, whatever, 4681. 4681 minus 1. So maybe we can consider these two numbers like A and B right here. Then we have 2 to the 2 to the AB minus 1. That equals 2 to the A raised to the B minus 1 by algebra rules that we all know and love. If not, go watch my fundamentals series, I guess. I'm like live solving SAT tests and stuff. And now, here's a delightful moment where we use the proof of conjecture 2 from... we use a proof of Velleman's conjecture 2, which we can see is going to be 2 to the A minus 1 times, let's write 2 to the A minus 1 times, like 1 plus 2 to the 2 plus 2 to the plus 2 to the A plus 2 to the 2A plus ... plus 2 to the AB. Or AB minus 1. I think that we're off by 1 on this, aren't we? We're off by 1. Like AB minus 1, or like A times B minus 1 or something. Anyways, like this second term doesn't really matter. The important part is that conjecture 2 says that this number is going to split this way. 2 to the A minus 1 times a huge number. So in this case, our A is 7, so then, therefore, we know that 2 to the 7 minus 1 divides the huge number. That, I'm just going to draw an arrow there. 2 to the 7 minus 1, you can run through your powers of 2 and then find that 2 to the 7 is 128, so then this number is 127, and boom, there's our answer. Cool. So I thought that was a really fun problem. I thought it was super, super dope. I enjoyed it a lot. I got stuck a little bit, and then ultimately, I had to go to the conjecture, and I thought of this fact, and it is actually really cool because it is also theorem 2 in George Andrews' book, in this number theory book. Quite literally, there's a coincidence between these two books, and who knows, maybe Velleman was referring to Andrews. Andrews proves this in general is always a theorem, he calls it. Andrews, which I will draw in this nice little blue-green color. Andrews' theorem 1-2 says, if x is any real number other than 1, then the sum of the sum of the powers of x from 0 to n minus 1, which is 1 plus x squared plus ... x to the n minus 1, equals x to the n minus 1 divided by x minus 1. So if you just multiply both sides by x minus 1, then this formula is exactly like what Velleman does with, but he only proves it for the case of 2, like a special case of x equals 2. But this is true for any real number. This is like a beautiful little identity, I think. And I've forgotten this one. Like in the last 15 years, I have forgotten this one. It is a super cool one. The proof is just FYI, proof by mathematical induction, also known as the dominoes method. I don't know if there's an E or not in dominoes. I hardly ever spell dominoes. Let's move on. So that's fun. Just wanted to quickly show that that's something that we did in the long second part of yesterday's stream. Today, I want to hell or high water write out the entire proof and statement again. Just repetition again and again. Spaced repetition, y'all. Like, this is how we're going to relearn math. We are going to relearn math by spaced repetition. We're going to restate quadratic reciprocity. Day 8, relearning number theory. Exclamation mark. All right, so it's like chapter 8, I believe. Nope, chapter 9. Close. We're getting closer and closer to memorizing this. Theorem 9.4. Whoops. How's it going, everybody? Oh, before we get started on this, I want to answer this question, something or other from Sam. Sam, let me know if you're still there. I apologize if I missed your comment. Yeah, this is kind of totally confusing to read, but nonetheless, it is in my book collection, the blue one, props to you and other math nerds who help people to understand. Hell yeah, dude. Yeah, I'm trying to put myself in your shoes as well. I'm trying to get in the same exact mindset. I'm going to write down a bunch of math right now that I do not remember. I do not understand. To me, it is also Greek. It is scary and confusing, but if you squint, there's something beautiful in it. You can tell that there's something interesting and beautiful, and it's something I want to understand again. So join me in the journey, and slowly over time, we will get there. We will understand quadratic reciprocity. We will understand the odd distinct theorem of Euler. We will understand Fermat's last theorem. Someday, maybe. We'll at least memorize and write out the proof without understanding what it means, and we can, over time, start to understand all these things. Cool, Sam. I'm glad that you're still there. Like and subscribe. Let me know what you like. Cool. Theorem 9.4. Also, hi, how's it going, Mateus? Let me know how to pronounce your name. Mateus, I believe. All right, Theorem 9.4, quadratic reciprocity law. I'm going to start using more shorthand. P, Q, I'm going to say P not Q odd primes. So I'm starting to in fact, I'm gonna do P not Q odd, because P and Q typically mean prime numbers, especially if we're looking at this book. So this is no longer verbatim what this book states it as. I'm trying to write it down in a way that's like more shorthand for my own brain. P not Q odd. It's so annoying that you often have to say odd prime. Let x and x let P be an odd prime. Like the only other case is 2. 2 is this like annoying counterexample to a lot of theorems. 2 is the most odd prime. It's the weirdest prime. That's a joke. That's a stupid joke. P not equal to Q odd, then P Legendre Q equals Q Legendre P unless P is congruent to Q. P congruent to Q, congruent to 3 mod 4. In which case P Legendre Q is not equal to Q Legendre P. Okay, I think that there is going to be a way to make this even shorter. Let's try again. P naught Q odd. Then P Legendre Q okay, give me 1 second. I need to take a very short little break. Okay, we are back. How's it going? All right, so let's try to get a more succinct way to write this. P Legendre Q equals Q Legendre P if and only if P. Oh wait, yeah. If and only if. If and only if it's not true that P is congruent to Q is congruent to 3 mod 4. So that's like a little awkward to rewrite. Like that is the logically equivalent way of saying the prior sentence, and then like distributing out this like negative, this like negation here is just super fiddly and tedious, and this is not a good path. Now I understand why Andrews writes it this way. Yeah. Okay, all right. Let's just keep it this way. I still feel like there's probably a cleaner way, or like a shorter, more succinct way, but I don't see it right now. So, all right, let's keep going. P not Q odd, then P Legendre Q equals Q Legendre P, unless they are both congruent to 3 mod 4, in which case they are not equal. Okay, so that's really interesting because, like, you don't even need to know what a Legendre is. Like, what is this Legendre symbol? This, like, P bar Q. It is not the same as the factorial. This kind of looks like the factorial. It is not the factorial, y'all. Okay, so it is not this thing. The Legendre symbol is something else that we will define in a moment here. But whatever it is, we've found some kind of deep connection between any two prime numbers. Like, that's kind of crazy. That's kind of really cool. Because as we've shown already by proving the fundamental theorem of arithmetic, the prime numbers are like the atoms of the universe. They are of the mathematical universe. Every single number can be expressed uniquely as a product of primes. Like there are only 20 whatever elements in the periodic table, right? There are the prime numbers. Unlike the elements, there are infinitely many prime numbers, but still, they are the indivisible constituents. Like, quite literally, the word indivisible constituents of every number. That's amazing. So here we have some kind of quadratic reciprocity. Like, I don't know what quadratic means here yet, but reciprocity means like whatever this symbol is, we can flip the two. Like P Legendre Q is Q Legendre P. Like you can flip the two in this symbol. Like what? What is that? And then we have some weird cool connection here where unless these two prime numbers like 5 and 7 or 5 and 11 or whatever and whatever 37 and let me show off how many primes I know. Who cares? Like any two odd distinct primes, like there's some kind of connection with 3 and with 4. Like 4 is 2 squared. Like, is that where quadratic refers, like, is coming in? Like, why is 2 squared so closely tied and connected to any other 2 odd primes? That's actually fascinating. That's actually very, very cool. And we don't even need to understand fully yet. I do want to understand because I want to understand what this statement says. Like, I want to understand this, but I can already see that there's something beautiful here. So, let's keep going. All right, proof. We are just going to do some muscle memory, and this time we're going to get through the whole thing, and tomorrow we're going to do more theorems that we actually understand. All right, so first, Andrews has a remark. I vaguely remember this. We're getting that muscle memory. There's a remark that we can rewrite this as -1 somehow, raised to a power. This theorem may be stated here. I'm going to start using more shorthand. This theorem equivalent to P Legendre Q multiplied by Q Legendre P equals -1 raised to the P minus 1 times Q minus 1 divided by 4. Whew! What? Okay, so both of those numbers are going to be even because they're odd primes, so subtracting one from an even gives you, or subtracting one from an odd gives you an even. So we know that the numerator is divisible by 4. And so this is -1 raised to some positive integer. Okay, well, we need to understand Legendre symbols a little bit more, I think, or pause and reflect to understand why that remark is equivalent, but that's not what we're doing. We're not understanding right now. We are rote memorizing. Next, proof. Let mu1 denote the number of integers in Q, 2Q, 1/2 P minus 1 times Q with negative least residues mod P. mu2 is similar. Oh, wait. Yeah. Yeah, mu2 similarly is the same thing with this set. Then we need some sort of powerful machine called Gauss's lemma. Gauss's lemma implies P Legendre Q equals -1 raised to the mu2. And Q Legendre P equals -1 raised to the mu1. Then, since P Legendre Q equals Q Legendre P, if and only if P Legendre Q, Q Legendre P. I don't even know if that's how you're supposed to pronounce it. That's how I pronounce it. Legendre PQ, or I like to say P Legendre Q. I don't know. I literally don't know. I did not learn this in university. I self-studied this. I don't think I've heard anybody pronounce this out loud, at least in a long time. If and only if that stuff, we see that P Legendre Q equals Q Legendre P if and only if -1 raised to the mu1 plus mu2 equals 1. I think I follow the logic roughly there in that step at least. Thus, to prove our theorem, can omit that, we must show mu1 plus mu2 odd if and only if P is congruent to Q, congruent to 3 mod 4. I'm very tempted to start writing 3 parentheses 4, but that's just a little too shorthand for me. I have seen that notation, though, in books. That does exist. Some people do write that. Brief aside, A divided by P, or A divided by B equals some number C. How do I want to say this? A equals KB plus C or something. What I'm trying to get at is that remainders is what residues are. Remainder. So like if you take 7 and you divide it by 2, 2 is 3 remainder 1, right? 2 times 3 is 6. 7 minus 6 is 1. So 7 equals 2 times 3 plus 1. This is the residue. It's the thing that's left over after dividing, after taking neat, even collections of the quotient, of the whatever, after dividing. How much do you have left over? Like, what is the remainder? That is what residues are. So it's kind of a more old-fashioned kind of word for remainder. Or just more number theoretic. We proceed, here's where we paused yesterday. We proceed geometrically. We shall, so I'm going to go back to writing kind of more precisely because this is the first time we're getting this part. We shall count in 2 ways. The lattice. Neat. Okay. We shall count in two ways the lattice points. That is, the points whose coordinates are integers inside a certain hexagon. What the hell? Okay, no, I do remember. I know exactly where this is going. Like, I remember that this thing can be proved by way of complex numbers, where complex numbers are going around a unit circle, and they're like these Gaussian integers with some sort of like angle theta or something, like zeta 1, zeta 2, zeta 3 or something. And so I think that we're going to draw in some way a hexagon, and then somehow this proof is equivalent to what I've seen in the past using complex numbers. My memory is so bad on this. I'm sure that I am speaking out of my ass, like quite literally. So let's keep going. That's my guess. That's where, but like so far, this is not exactly what I was expecting. Inside a certain hexagon, the first count will show. Okay, I'll just read it out loud and then write it. Why don't we do that? That's going to be smarter. Coffee break. What do you all think? Is this interesting? Is this fun? Like, to hear some pure mathematics that you don't understand and I don't completely understand, but I sort of understand a tiny bit. Is this entertaining? At least? Like, I'm guessing that nobody in the chat right now knows completely understands what this proof is doing. Sometimes we do have grad students, but even them, I think the grad students who are regulars are not number theorists. So, all right, let's just read this out like a bedtime story. The first count will show that there are odd number of lattice points in the hexagon if and only if P is congruent to Q is congruent to 3 mod 4. The second count will show, let's pause, let's restart the whole paragraph so we have context. We proceed geometrically. We shall count in two ways the lattice points, that is, the points whose coordinates are integers, inside a certain hexagon. Inside a certain hexagon. The first count will show that there are The first count will show that there are an odd number of lattice points in the hexagon if and only if P is congruent to Q is congruent to 3 mod 4. The second count will show that there are mu1 plus mu2 lattice points inside the hexagon. The two counts together will show that mu1 plus mu2 is odd if and only if P is congruent to Q and 3 mod 4. In the first quadrant of the xy plane, we consider the hexagon H with vertices A, B, C, D, E, F that lie on the rectangle AGDJ, bounded by the coordinate axes and the lines x equals p divided by 2 and y equals q divided by 2, as shown in figure 9-1. This is not the proof that I've seen in the past. So we get this neat diagram, okay? We get some diagram of two lines. This is not the proof I've seen, for sure. Line EF is defined by this equation, and line BC is defined by this other equation. The line BC has x-intercept 1/2, 0, and line EF has y-intercept 0, comma 1/2. Both are parallel to the diagonal AD. This is super cool. This is a geometric proof of this. The coordinates of the points that lie in the interior of H must satisfy 4 inequalities. Note that if Mn is any lattice point in the interior of H, then so is p plus 1 divided by 2 minus m, q plus 1 divided by 2 minus n. We can verify this by substituting these coordinates into the 4 inequalities of 9(3-2). Now see that the greatest common, the point Mn is this thing. If and only if m is this and n is this and p is this is a lattice point, if and only if p is congruent to q and 3 mod 4. Thus the pairing of the point Mn with this thing shows that the number of lattice points in H is odd if and only if p is congruent to q and 3 mod 4. Now let us consider the lattice points in H from a different point of view. It is clear that there are no lattice points on the diagonal. If Mn is a lattice point below the diagonal, then blah, 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 some calculations. We see that in this case, NP has a negative least residue mod Q, namely NP minus QM. Conversely, something or other, ... mu2 is the number of integers in that set. In exactly the same way, we find mu1 lattice points in H, and we conclude that mu1 plus mu2 is odd if and only if p is congruent to q and 3 mod 4. Thus, the quadratic reciprocity law is proved. Whoa, I did not expect this. I was expecting a very different proof. I don't know if I want to learn this proof. I know that there's a more elegant proof. I just know that there's an absolutely more elegant proof. I don't know if this is the one I want to memorize. This is not the one. I feel good about saying that. I'm very curious. Historically, is this Gauss's first proof? He proved it 6 times. Is this even Gauss's proof? Because this is one of the most reproven statements in math, as I understand it. This has many, many proofs out there. The same way that we have lots of proofs of the fact that there are infinitely many primes, or the Pythagorean theorem. There are many, many proofs of those wonderful, beautiful gems of mathematics. So I haven't seen this one before. It's not the one I've seen. I liked the one I learned when I did a independent study proving this. And there's no historical note in Andrews about whose proof is this. I wish that he made a statement about this. Maybe it's at the beginning. So, yeah, great mathematicians such as Leonhard Euler and Legendre were baffled by it. So the guy who invented this whole fancy notation, Legendre, tried to prove this claim, this conjecture, and couldn't figure out how to prove it. So that's really cool. And then Gauss, being the badass that he was, he proved it when he was only 19 years old. That's freaking cool. And because this theorem is of fundamental importance in number theory, Gauss returned to study it many times throughout his life, and he gave at least 6 different proofs. Yeah, there's Gauss's lemma seems to be important no matter what. Yeah, there's no historical note on where this proof comes from. I just know it's not the most elegant one that I've seen. At least, maybe I just don't like geometry. I'm just going to come out and say it. Maybe I just don't like geometry as much as complex numbers. You know, like this stuff is like human taste. Like how like it's very hard to have an elegance meter and actually scientifically measure how elegant is this proof compared to this other proof. Um, I think that this proof in Andrews is more quote unquote elementary, meaning it does not have as many prerequisites as you don't have to build such heavy, big machines as the complex numbers and maybe even some complex analysis. Yeah, so this book is more self-contained and assumes that you remember a little bit about geometry, but it's just kind of tedious, like compared to what I remember. I'm not going to write all that out. This is a longer proof than I remembered or than I expected. I'm sorry, y'all. So I keep saying that we're going to write out the entire thing or else my fingers are going to fall off. I hope I did not just damn my fingers to fall off. We're not going to write this whole thing. But we're going to walk backwards a little bit, and we will write out Gauss's lemma, because I believe that even in the other proofs, you need this thing. Gauss's lemma. We will get this one, and maybe even more importantly, we're going to figure out what this Legendre symbol is, okay? I want to understand what the hell is this symbol that we've been writing so often. Let's take a step back. What's a good color? I want to use yellow now. Yeah, Legendre and Jacobi symbols are related. I remember signs of numbers. Whew. Okay. 9-2, the Legendre symbol. Legendre symbol. Definition 9-1. If P is an odd prime, then A Legendre P equals either 1, 0, or -1. I vaguely remember this now. 1 if A is a quadratic. Okay, here we go. If A is a quadratic residue mod P. 0 if P divides A, and then -1 otherwise. Okay, well, it turns out that we're going to have to keep pulling this thread. What is a quadratic residue? Let's pause and actually try to walk back a little, like enough until we start to actually really understand these definitions. So this is what mathematics is like. Like, you open up a book, you open up a paper, and you try to understand the thing, and then they refer to some term that you've never heard of before, and they say, see this other paper, see this other book for a definition of this thing, and then you go look at that book, and you keep doing that, walking backwards in the chain of crazy definitions that mathematicians have created until you start to understand something. And when you get that little wedge and you're like, aha, I think I understand that part, then you can start walking forward again. You skip the details on the results in between, and then you try to understand the thing that you're actually trying to get. So, like, mathematics is taught in undergraduate degrees as if it were this beautiful axiomatic system where every single step is perfectly understood and a result of prior results, all coming down to the axioms of Euclid or Peano or ZFC or whatever. That is true, but a working mathematician does not go all the way back to the axioms. You do not understand your research field from the axioms. You assume at some point there's this black box, and you take the definitions and you assume, the whole path of the graph from the axioms to that part of the humongous tree of mathematics. And you take that as a given, and then you work from there. Like assuming that the Riemann hypothesis is true, then blah, blah, blah. Like, okay, we haven't yet proven the Riemann hypothesis. Who knows if or when we ever will, but I'm going to assume this thing, and then my work depends on this preliminary result. That is more what real world mathematics is like. And that's what I'm trying to simulate a little bit here as I relearn number theory. Like, I don't completely understand, or I didn't understand. Like, I kind of sort of understood kind of what this is saying. Like, I could see at least that there's something beautiful there, and I understand certainly some parts, like what congruences are. You may not yet, but you will. And I know I've seen this Legendre symbol before. I at least know how to pronounce it. But we have to walk back and try to get it. So we see the definition of a Legendre symbol here. Did I not write out the very last sentence in this thing? Definition 9.1. Yeah, okay, it just didn't put it in the box. Then the Legendre symbol, A by P, is... This is kind of implicit in what Andrews says, like this parenthetical, then the Legendre symbol, A Legendre P, is defined as this. But when trying to understand that definition, we see that there's another definition, at least that I need. What is a quadratic residue? That is something about squares. I'm pretty confident. What the hell is... Okay, we only need one step back, one page back. Euler's criterion. Let's, I want to get a rough sketch of an idea of how one would prove quadratic reciprocity, even if I don't know the details. Like, what are the big picture ideas? 9-1. The chapter is called Euler's, the section is called Euler's criterion. Again, Euler studied some of this math, and he got stuck and wasn't able to get the quadratic reciprocity law. But he understood some of this stuff and tried to study it and made some results. Our first step... Oh, wait. Let's get this preliminary. No. How are we on time? I have until 12. I think we can get this. In our study of congruences, we have discussed the circumstances under which AX is congruent to B mod C has solutions. The next simplest congruence is X squared congruent to B mod N. The ability to solve this quadratic congruence will in most cases enable us to determine whether a quadratic congruence of the form ax squared plus bx plus c equals 0 is congruent to 0 mod d, whether that has solutions. Okay, so I'm going to summarize this for the sake of our own understanding, our own active learning of mathematics, and for the sake of time. So, TLDR, we want to understand whether ax squared plus bx plus c congruent to 0 mod d has solutions. Okay. So this is cool because I can point to, this sounds super familiar. Remember, quadratic equation from high school or middle school or whenever you learn it. Instead of an equal, we all remember from algebra, from middle school algebra, that this is equivalent to the solutions x equals negative b plus or minus the square root of the discriminant plus or minus the square root of b squared minus 4ac, b squared minus 4ac, all over 2a. Right? Pop goes the weasel. So this is the quadratic formula. And this is when ax squared plus bx plus c is equal to 0. What we have here is instead we have this triple equal. What that is a congruence. So we have that triple equal that's different, and we have this thing mod d. So my TLDR is that the left-hand side equals k times d, also known as k times d plus 0, for some k, for some integer k, that this equation ax squared plus bx plus c is a multiple of d. So maybe d is 5. And then we're trying to understand when the equation ax squared plus bx plus c, like when does this have solutions? Like whether that solution is 0, 5, 10, 15, ... Like we're trying to understand when we can solve this type of equation. Again, like we're talking about remainders. We are talking about these things called residues. Number theory is all about studying, number theory is about studying divisibility a lot. Like you really are understanding divisibility and like when the remainder is 0 or not 0, etc. All right, so there, now in my head, I now have a much better grasp of what quadratic residues are. They are solving the quadratic equation in modular arithmetic. I think that that's accurate. I think that that's a decent summary. All right, then we want to understand that. Blah, blah, blah. So that's the motivation. Our first step is to develop a test for determining whether there exists an integer x such that x squared is congruent to a mod p. So this is kind of like the simplest quadratic equation, right? X squared equals or is congruent to a number, and like the modulus is not any number d, any integer d, but it is actually a prime p. Cool. So then it says, as I expected, where p is prime, and okay, GCD of A and P is equal to 1. Okay, well, if P is prime and the greatest common divisor of the two is 1, then that just means A is not a multiple of P, right? So then, I don't know. This is like saying A is not 0. I think that would be simpler. No. Yeah, right? That's kind of weird. Maybe I'm misunderstanding something. But let's move on. If P does not divide A, and this equation and the equation has a solution, we shall say that A is a quadratic residue modulo P. Quadratic residue. Okay, so we're getting somewhere, y'all. We're getting somewhere. I could either write down this example, which would be very helpful. Nobody understands what I'm talking about, including myself. Or we could write down the Legendre symbol more. We already wrote down the Legendre symbol. And we already defined quadratic residue. So now we understand somewhat. This symbol A bar P, whatever that is, Legendre P, it equals 1 if A is a quadratic residue mod P. Okay, so if A is a quadratic residue mod P means that there are solutions such that x squared is congruent to A mod P. Is that the same? Yeah. If the equation has any solution, if the equation has a solution, then A is a quadratic residue mod P. So that is exactly it. Has any solutions. Neat. So if P is an odd prime, now I completely, fully understand this symbol, and I feel like I accomplished something with my free time today. That's nice. That's great. Let's get some bonus extra credit, and we got about 10 minutes. This is fun for me, y'all. I have no idea if it's fun for anybody else. Y'all just want me to get back to linear algebra. You want me to learn how to build AI. I know. Me too. But I want to have fun along the way and study some number theory. It's good for your brain. It's like you're eating your vegetables or something. It's just, it makes you think. It makes you think hard and try to understand something hard before you just calculate matrices. All right. Example. Let's get an example. Let's change color because that's fun. Let's get blue. Example 9-1. Maybe P is 7 as an example. Since 1, 4, and 9 are perfect squares not divisible by 7, they are quadratic residues mod 7. Okay, I wanted to write a couple things as we went. So they're perfect squares. So a perfect square means that it is a square of a prime. Is that how it works? Yeah, is a perfect square a square of a prime? Or coprime factors, something like that. Anyways, like, I don't know if I guess 1 is considered a perfect square. Apparently. They are quadratic residues mod 7. So then, what that sentence says is that there exists, fancy symbol, there exists an integer x such that there is a solution to this equation. X squared is congruent to 4 mod 7. X squared is congruent to 9 mod 7. Okay? Andrews is probably going to show that these are the only ones, but at least right now we can pause and try to actively think, what does that mean? Can we solve these equations? So, yes, 7 does not divide any of those numbers, 1, 4, and 9. So I think that we can figure out what these solutions could be. Well, the first one's easy. X equals 1 satisfies, I'm just going to say x equals 1. In this case, well, I suppose x equals 2 works. And in this case, what's wrong with 3? Yeah, I mean, these are all fairly straightforward examples, right? Like, so x squared is congruent to 9 mod 7 is the same as saying that x squared is congruent to 2 mod 7 because 9 is 7 plus 2, like the residue, the remainder of 9 after dividing by 7 is 2. Yeah, I don't know. These don't seem that interesting. We still get the same solutions, 1, 2, and 3. And maybe that's just like super explicit in perfect squares. Maybe that's what he's trying to get at. I don't know. Okay. Now we're getting somewhere a little bit more interesting, I think. Then he says any integer congruent to one of these squares modulo 7 is also a quadratic residue mod 7. Okay, any integer congruent to one of those squares is also a quadratic residue mod 7. So then we are saying that there exist solutions x for x squared is congruent to, well, any integer congruent to one of these squares mod 7 is also quadratic residue. Yeah. Like we also have solutions to x squared is congruent to 8 mod 7. This actually isn't as interesting as I thought. X squared congruent to 7 times 4, or maybe not 7 times 4, but 7 plus 4 is 13. Or no, it's not. What am I doing? It's 11. Mod 7. And x squared congruent to 2, as I wrote earlier, or maybe subtracting another 7, x squared congruent to negative 5. Like, I don't know, that seems kind of... That seems reasonable. That makes sense. So he says, hence, negative 6, 2, and 11 are all... Did I do my math wrong? Negative 6? Shouldn't we get negative 5? Well, I guess negative 6 is based on one of the other ones. Negative 6, 2, and 11 are all quadratic residues mod 7. Although 49 is a perfect square, it is not a quadratic residue. Theorem 9.1. A is a quadratic residue mod P if and only if A raised to the P minus 1 divided by 2 is congruent to 1 mod P. Okay, so this is an interesting fact that's going to require a proof. And this is called Euler's criterion. Okay, so in order to prove quadratic reciprocity, you need to prove Euler's criterion. And after you have Euler's criterion, you get a little useful corollary. And then based on both of those, you define the Legendre symbol, and then you prove something called Gauss's lemma, which I'm going to very quickly try to write. Theorem 9.3. Maybe I already did. I don't remember. Gauss's lemma. This thing is important in the proof for quadratic reciprocity. Let GCD, the greatest common divisor of M and P, equal 1, where P is an odd prime, and let mu be the number of integers in M to M 1/2 P minus 1 times M, whose least residues mod P are negative. Then, now we get a useful little calculation, a useful way to write the Legendre symbol. Okay, and I vaguely remember how we rewrote Legendre symbols all the time as -1 to the mu1 and -1 to the mu1 plus mu2 in the quadratic reciprocity proof. So that's cool. All right, how to prove quadratic reciprocity. You prove Euler's criterion. Then you define the Legendre symbol. then you prove Gauss's lemma, and then you prove quadratic reciprocity by a geometric argument. That's the best that we can do for now. I will try to find the proof that I've seen in the past that that used I believe it was a field of the Gaussian integers, which are complex numbers, and you multiply two of them and you get another one in this finite field. And you could think of it as points based on a repeating angle, like a multiplication of an angle, I believe, such that there are like a prime number of them in the unit circle. And I just remember it being a lot nicer than what we saw briefly in the book today. So this concludes my weird little mini series on quadratic reciprocity. We will be back to it in the future. Who knows? 6 months in the future, someday. This time around, I tried to just write it down, refresh my memory a little bit, see the proof, try to understand a little bit, skimming through this mathematics, and recognizing we're not ready yet. We are not ready yet, but we will get there. I'm trying to skip forward, see a little bit of math, understand whether or not we can understand it today. And I understand a little bit. I learned a lot, and I hope you did too. Thank you for watching. And now we're going to go back to the other end, and we're going to keep working forward with math that we totally, fully, completely understand. So join me. Please let me know in the comment section if you enjoyed this. Am I a big dummy? Who out there is watching this and knows everything I'm doing and understands all of it and is just cackling oh, look at this weirdo trying to jump to semester 2 of number theory without doing the preliminaries. It is a weird approach, I believe. Yeah, let me know. Let me know if you've seen this before. Let me know how I'm doing, if you can give me a fair assessment on that. And I'm even more interested, let me know if you're enjoying this and following any of it, or just enjoying it as entertainment if you haven't seen any of this before. Thank you again, everybody, for watching. I'll be back in a couple of hours, and we'll just be live practicing and solving problems from this book while listening to YouTube videos. So, cheers.